Good morning, everyone. So this is my next lecture on semiconductor devices, and this is in continuation with the lecture number 20, which is basically based on MOSFET. So here we are going to deal with different type of semiconductor devices like LEDs and lasers. So this is lecture number 21. So we have this is basic LED operation. So we know LED is what? Light emitting diodes. So in the first lecture I have discussed about these semiconductor devices are basically made up of aluminum, gallium arsenide or different third or fifth group elements. So by joining these third and fifth group elements, we can create our LEDs, lasers and different type of photodiodes. So basically what is LED? LEDs have is known as light emitting diodes, and it is basically a PN junction which acts as the active or the recombination region. So it is similar, somewhat similar to the PN junction. In LED we have a P type of semiconductor and N type of semiconductor. We join that and we create a LED. So basically when a PN junction is forward biased, electrons and holes recombine either radiatively, which is basically emitting photons, or non-radiatively, which is basically emitting heat. So we have to see here the two concepts, that is first one is the radiatively and second one is the non-radiatively. So when there is radiation, there is emission of light. When there is not radiation, then there is emission of heat. So this is simple LED operation. We can see from the diagram itself that we have in the lower region, which is valence band, and in the conduction band we are having two energy levels, that is E1 you can say, or this is your E2. So in between E1 and E2 there is always a gap which is basically known as band gap. So for silicon we know the band gap is around 1.0 electron volt, and for germanium it is around 0.3 electron volt or something electron volt. So there is a more number of holes in the valence band initially, and we have conduction band, so more number of electrons in the conduction band. So whenever there is a operation of recombination of electron and hole pair, there is emission of light. So emitted wavelength depends on band gap energy. So whatever the band gap energy we are considering here, that is suppose it is 1.0 electron volt. So obviously the electrons have to cross this particular energy gap between the valence and the conduction band to transmit from valence band to conduction band. So electron will move or jump from valence band to conduction band when we provide a particular energy of 1.0 electron volt. So emitted wavelength depends on band gap energy here. So transition takes place from any energy state in either band to any other state in other band. So we have already discussed about multiple energy levels in a particular conduction or the valence band. So the electron can move from one energy band to another energy band. Here it is moving from valence band to conduction band. In the conduction band also it will move from lower energy state to upper energy state. So it results in a range of wavelength produced spontaneous emission. So there is a new term which is spontaneous. So LED is basically based on spontaneous emission process, while the lasers are basically based on stimulated emission process. If there is no stimulated emission process, there is no working of laser, or the laser will not work. So typically the wavelength of the is in the range of more than 80 nanometer for the LED. So we have drawn here three figures. The first figure shows the valence and the conduction band and having a energy band gap between both these 1.0 electron volt. The second figure is for providing you the concept of the homojunction, because if it is homojunction means there is only one junction. So between P and N there is only one junction. There is another concept which is called as heterojunction. So in that case we have two junctions or more than one junctions. So the electrons in the N region or in the conduction band, in the N region of the conduction band, it will move towards the valence band, conduction band in the P region. Similarly, the holes will be moved from P region in the valence band to the N region in the conduction band. So when you provide the forward biasing, the transition of electrons will from N to P side, and similarly the holes from P to N side. and there is emission of light. So this is your emission of light h nu, which gives you the light in the form of the light. Obviously the LED will give you the light because it has a radiation or radiative type of nature process. So if we see about this diagram, that there is how to form a LED or light emitting semiconductor. So if you see here, there is a below region which is called as substrate, in the same way as we have done in the MOSFET. So below region is substrate. There are two region, obviously P and N type of region, and in between P and N type of region there is we know there is depletion region, but here we called it as active region. So there is an active region. So light will be, if you provide forward biasing, the electron hole pair will move, or the electron will move from the N region to P region, and similarly the holes will move from P region to N region, and there will be emission of light from the body of the particular LED. So here we have a table showing the materials like with which we can form our LED, that is aluminum gallium arsenide, aluminum gallium indium phosphide, gallium arsenide, indium gallium arsenide, indium gallium arsenide phosphide. So these have wavelength range around, if we talk about aluminum gallium indium phosphide, which is a quaternary compound, having a wavelength range of 0.61 to 0.68 and having a band gap energy around 1.82 to 1.94. Similarly for gallium arsenide, it is 0.9 and band gap energy is 1.4. So we have a list of material with which we can form our light emitting semiconductors having different wavelengths. So light is emitted at the site of the carrier recombination, which is primarily close to the junction. So the amount of radiative recombination and the emission area within the structure is dependent upon the semiconductor material we are using and what kind of fabrication we are using in the device. So what kind of wavelength it is emitting, it depends purely on the material type. If we are using gallium arsenide, it will emit wavelength of 0.9. If we are using indium gallium arsenide, it will emit wavelength of 1.0 to 1.3. So we have this type of material wavelength and band gap table. In the tabular form, we can see easily the differences between what type of material we are using and what kind of wavelength we are achieving from the light emitting diodes. So next we have light source material. So most of the semiconductor light sources contain, as we have already discussed, contain third and fifth ternary and quaternary compounds. So as an example, we have gallium aluminum arsenide. So gallium has a proportion of 1 minus X and aluminum has a portion of X arsenide. So by varying X, it is possible to control the band gap energy and thereby the emission wavelength over the range of from 800 nanometer to 900 nanometer. So the spectral width is around here 20 to 40 nanometer, which is obviously wider than as compared to the lasers or lasers. So the third point is here for quaternary compound. So in quaternary compound we have 4 different type of compound, that is indium gallium arsenide phosphide. Obviously if we are taking fraction of gallium is X, then indium is 1 minus X. Similarly fraction of arsenide is Y, then phosphide has 1 minus Y. So by changing this value of X and Y is approximately 2.2X, the emission wavelength can be controlled over a range of 920 nanometer to 1600 nanometer. So the spectral width varies from 70 nanometer to 180 nanometer when wavelength changes from 1300 nanometer to 1600 nanometer. So here the spectral width is much higher as compared to the ternary compounds. So at 850 nanometer region, gallium arsenide and aluminum gallium arsenide. Similarly, for 1300 to 1550 nanometer region, we can use indium gallium arsenide phosphide and indium phosphide. So these type of regions for different wavelength region, if we want to operate in LED to be operated in different region like 850 nanometer, we have to make sure that the material used for constructing LED is gallium arsenide and aluminum gallium arsenide. Similarly, for operating LED in the or having a wavelength from the LED in between 1300 to 1550 nanometer, we require this kind of material, which is indium gallium arsenide phosphide and indium phosphide. So now we are discussing about what is homojunction. So homojunctions are basically having only one junction. So it can be made from P and N type of the same material. So in the heterojunction we have two junctions, or we can have different materials for the p and n type. So in the homojunction we have p type of gallium arsenide, similarly n type of gallium arsenide. If we dope the p type of gallium arsenide with heavy doping of the trivalent impurities, so we have gallium arsenide, p plus type of gallium arsenide, and the depletion region or the active region is of p type of gallium arsenide. Similarly n type of gallium arsenide is there. So if we see the structure and index of refraction in gallium arsenide with a junction width d, we can find out this type of structure. It's a kind of a well structure. So carriers are not confined here in this type of structure, and light is also not confined here. So LED should have a high radiance, light intensity, fast response time, and a high quantum efficiency for fiber optic communication systems, which is basically the application of LED in fiber optic communication system. So these are basic characteristic of the LEDs which is responsible to have these LEDs to work to having a role in optic communication system. So if we talk about heterojunction, heterojunction is the advanced junction design to reduce the diffraction loss in the optical cavity. So this is accomplished by modification in the material to control the index of refraction of the cavity and the width of the junction. The index of refraction of the material depends upon the impurity used and the doping level. So whatever kind of impurity you are using here, for example, if we are using trivalent impurities or pentavalent impurities, according to that we have the index of refraction. So the heterojunction region is actually lightly doped with p type material and has the highest index of refraction. Similarly, the n type material and the more heavily doped p type material both have lower indices of refraction. So this produces a light pipe effect that helps to confine the light to the active region, and that's why the confinement factor in the case of the heterojunction is much more higher as compared to the homojunction. In the homojunction, this index difference is very low and much light is lost here. So double or single heterostructure junction with better light output. So we can use in different semiconductor devices in industrial application LED with heterojunctions. So if we are using heterojunction, we have a more index difference in the index of refraction, and that's why the light is confined in the structure. So if we talk about heterojunction more, different p and n type of materials. So we have what characteristic we are finding in the case of the heterojunction. Carriers are easily confined in the case of the heterojunction. Light, if carriers are confined, then obviously light is also confined. Single heterojunction and double heterojunction can be used for different industrial applications. A heterojunction is basically a junction between two different semiconductors with different band gap energies. So the difference in band gap energies creates a one wave barrier. Charge carriers, electrons or holes are attracted over the barrier from the material of higher band gap energy to the lower band gap energy. So if we see the diagram below here, so we have n type of indium phosphide, and we have at the upper side we have p type of indium phosphide, and the active region is made up of n type of indium gallium arsenide phosphide. So these you can see here that this is the one region and the second is this junction. So there are two junctions basically. One is from in between p indium phosphide and n indium gallium arsenide phosphide, and another one is in between n indium gallium arsenide phosphide and n indium phosphide. So if we see the difference between the index of refraction, then obviously the difference between the index of refraction is much higher as compared to the homojunction, and that's why the light is confined more in the structure. So gallium arsenide, aluminum gallium arsenide, single heterojunction is shown here, and that's why you have a much more confinement factor as compared to the homojunction. So if we talk about double heterojunction, when a layer of material with a lower band gap energy is sandwiched between layers of material with a higher band gap energies, a double heterojunction is formed. So if we are taking about two lower index of refraction or lower band gap energy materials, and in between there is a higher energy band gap material, then there will be formation of the heterojunction. So this is called as double heterojunction because there are two heterojunctions present, one on each side of the active material. So as we have seen in the last figure, we have both gallium arsenide n type and p type, and in between there is indium gallium arsenide phosphide layer. So there are two type of different junctions is present in the structure. So the double heterojunction forms a barrier which restricts the region of electron hole recombination to the lower band gap material, and this region is then called as the active region. That's why the region in between the two is called as active region. You can see from the last figure I have shown that p indium phosphide and n indium phosphide, and in between there is n indium gallium arsenide phosphide active region. So this region is basically your active region. Similarly, here we have p plus aluminum gallium arsenide and gallium A1 minus X arsenide and gallium arsenide active region, and n type of gallium arsenide. So this is also your active region. So we have a obviously the depletion or the active region width is here termed as D, and we can see the difference between the index of refraction between P plus and P and P and N, and that's why the confinement is more. So in the heterojunction we have confinement which is high, radiance is high. So coming to laser diodes, so laser is, as we know, laser is having an acronym for light amplification by stimulated emission of radiation. So if we compare both LEDs and lasers, so LED has non-coherent light, the laser has coherent light, it has a narrow beam width, the LED has wider beam width. As we have seen already, the LED has a spectral width around 20 to 40 nanometer. So LEDs have much higher width as compared to the laser. The second point is the coherent light, which is very important factor in the case of the laser diode. So laser diode has coherent light, it has the light has same frequency, same phase and same polarization also. So lasers can produce high output power in fiber optic communication. If you use here in fiber optic communication applications, which is basically having much wider use of lasers. So semiconductors lasers having power more than 20 milliwatts are available. As laser light is coherent, a high percentage, that is 50 to 80%, can be coupled into the fiber core. So as the beam is also narrower as compared to the LEDs in the case of the laser, and also we have the coherent light. So we have the same frequency, same phase and same polarization in the case of the laser, and the beam width is also narrow. That's why we can easily couple lasers with fibers. So there is one advantage. So laser plus fiber is more efficient method to couple light. While if you are using LEDs plus fiber, so obviously the beam width of the LEDs are much wider. So that's why it is not more efficient to couple light into from the LED to the fiber. So that's why we use lasers in different as a semiconductor device in different optical fiber projects or optical fiber industrial applications. So if we see the basic operation of the lasers, fundamental lasing operation. So we have three phenomena in the laser. First one is the absorption, second one is the spontaneous emission, and the third one is the stimulated emission. So in the case of the LED, we have only one factor which is called as spontaneous emission, because there is no requirement of light from the outside. External factor is not required for LED to work on. But in the case of the laser, we require a light to fall on the electrons in the valence band or in the lower energy level to make it jump to the higher energy level. So if we see from the diagram, the first diagram shows for the absorption phenomena. So here we have E0 energy level and E1 energy level at the higher level. The difference between the two energy level, which is given by Einstein relation, which is E is equivalent to h nu. So the difference is E1 minus E naught. So H nu is your photons which we hit the photon to particular electron or atom in the lower energy level to make it to jump to higher energy level. So this electron is basically absorb the light and it will move towards the higher energy level. So here we are showing the after diagram which is having the electron in the conduction band in the higher energy level. Similarly, for the spontaneous emission, the electron has came to higher energy level, then it will fall back to the lower energy level because it has a limited lifetime. So as the electrons will fall to the lower energy state, it will again emit some light which is in the form of the light, basically H nu, and it has obviously a difference of energy which is E1 minus E naught. In the case of the stimulated emission, we have to firstly hit the photon to this particular atom or the electron in the high energy state to make it to jump to the lower energy state, then it will emit one photon. So in the case of stimulated emission, we have one photon incident and two photons which we are getting. So obviously the gain factor in the case of stimulated emission is much higher because from one photon we are creating two photons at the emission process. So if we see about the difference between the lasers and the LEDs are very simple, having a simple structure. It has spontaneous emission only, but in the case of the laser we have all these three phenomena, and obviously the rate of the forward, or you can say the rate of the upward transition, the rate of the downward transition should be equal in the case of the laser. So rate of upward transition is equivalent to rate of downward transition in the case of the lasers. So the laser is basically based on population inversion process. Until unless there will be a more population of electrons in the high energy level, there will be no emission of light due to stimulated emission or spontaneous emission, and there will be less, if there is less light or lasing action will not take place. So these three phenomena basically holds the whole laser operation: absorption, spontaneous emission and stimulated emission. So this particular slide shows you the condition for large stimulated emission, because we require large stimulated emission. So initially the electrons are in the lower energy level, which is your E naught, but after some time when there is more number of photon will be incident on the lower energy level and it will be absorbed by the lower energy level electrons, it will move towards the high energy level or excited towards the high energy level. So there will be more number of electrons in the high energy level. The electrons can fall down spontaneously and on its own, or by stimulated emission, by having a photon incident on the higher energy level to make it to jump to lower energy level. So we have a cavity type of structure in the case of the laser. More number of electrons are present in the higher energy level and there will be lasing action will take place. So all these three processes occur together with a balance between absorption and emission, two conditions to be satisfied for stimulated emission to overwhelm the spontaneous emission. So the population of excited level should be greater than that of the lower energy level. If the population is not higher, there will be no spontaneous emission and obviously no stimulated emission will occur. More radiation density in the medium should be very large, and obviously rho, the value of the rho or the radiation density is denoted by rho. It should be very, radiation density should be very large. So this radiation density factor must be large enough so that there will be more emission of electrons. So next we have on the basic principle on which the laser or the lasing action will based on. So it is called as population inversion. So we have these three phenomena: absorption, spontaneous emission, stimulated emission. So basically this figure shows the E1 and E2 two energy levels and number of density of electrons. In the lower energy level is N1 and the higher energy level the density of electrons is N2. So at thermal equilibrium, photon absorption and emission process takes place side by side. So until unless there is at T equivalent to 0, or you can say at thermal equilibrium, when there is no rise in the temperature, the electrons having the photons absorption and the emission process takes place side by side, because N1 is greater than N2, and in this case absorption dominates. So laser operation requires stimulated emission exclusively, and to achieve this, majority of atoms should be at higher energy level than at lower energy level. So energy is to be supplied to the laser medium to raise the number of electrons from lower energy level to high energy level, and this process, particular process by which these electrons will absorb some energy and they will transmit from lower energy level to high energy level, this process is called as pumping. So this particular process is called pumping. Pumping, with the help of the pumping, the absorbed electron or the absorbed photon to the electron will make the electron to move from lower energy state to high energy state. After that, these two processes will occur, that is the spontaneous emission and stimulated emission. So this is the principle on which, so initially what will happen? Initially the number of electrons are less in the conduction band or in the high energy level, but after some time the number of electrons in the high energy level keeps on increasing. So until and unless it keeps on increasing, only in that case the stimulated or the spontaneous emission will occur. So in stimulated emission, incident and stimulated photons will have identical energy, identical wavelength or narrow line width, as we have already discussed about, that is having a coherent type of phenomena will occur in the case of the laser. Identical direction, narrow beam width, identical phase, coherence and identical polarization. So we have both the photons which are emitted from the stimulated emission, they have the same frequency, the same phase and the same state of polarization. So basic laser structure we can see here, that as a Fabry-Perot laser. So laser has been act as a cavity here. So homojunction device with cleaved ends demands for threshold current density here. So we have two mirror structures, one at the initial rear side or in the far side. So in between the lasing action will take place. So we have already discussed about N gallium arsenide and P gallium arsenide type of material. In between there is an active region. So this is your active region. So obviously the light will be emitted from these regions. So these mirrors are used for having the electrons and hole pair to make it sure that electrons will hit this mirror and then come back to the active region. So there will be a gain process in the active region, due to which there is emission of light in the structure. So these mirrors are basically for recycle phonons or the photons in the structure, in the cavity, and this will give you a coherent type of light in the case of the lasers. So up to this we have discussed about LEDs and lasers. We discussed about more about lasers, and then we discuss about photodiodes. So photodiodes are also a major part of the semiconductor devices, and these devices are also used for detecting your photon or the light on the photo detector and then convert it into a particular electrical energy. So we see how these photodiodes, either it can be a pin or avalanche type of photodiode we can use. These photodiodes are used basically for converting optical energy into an electrical form. So thank you so much. We will meet you in the next